All right. So the only thing left to do here now is to prove Grunwald's inequality. And I like this proof. Like I said, I like it because it's some clever calculus stuff. It's not really difficult, but it is a bit odd, and it takes some wrapping your head around. We're going to start the proof of the theorem right here with what I've already written on the screen by letting capital U of t equal the integral that's on the right-hand side of Grunwald's inequality. So we're letting capital U of t equal c plus the integral from 0 to t of k u of s ds. And I just want to also note, because we're going to use this in a bit, that by the hypothesis of Grunwald's inequality, little u of t is less than or equal to capital U of t. All right, so that's where we're at here. And the first thing I want to do is I want to take the derivative of capital U and see what we get. And that's very easy. That's just the fundamental theorem of calculus. And so that is k u of little u of t. And so this is by fundamental theorem of calculus. The astute watcher will notice that I have changed a 0 to the bottom of that instead of a t sub 0, but that is totally irrelevant. I've just done that for ease. All right, so that's the first thing I want to do, is just compute the derivative of that. The second thing I want to do is to divide u prime by u. And that seems a bit strange. So I get capital U prime of t divided by u capital U of t. And that is equal to k times little u of t divided by capital U of t. And let's think about that second item there, the little u divided by big U. Little u in the numerator is less than or equal to big U in the denominator, and by the hypothesis of the theorem. So this stuff right here, since little u is less than or equal to big U, this stuff here is less than or equal to 1, making what's on the right side of that less than or equal to k. Okay, so that just followed from the hypothesis on the of that odd inequality that u was bounded by that integral, the hypothesis of Grunwald's inequality. So why did I do that? Well, I did that because on the left-hand side, I can express the left-hand side as a derivative. The left-hand side is the same as the derivative with respect to t of the natural log of capital U of t. And I know that that is still less than or equal to k. Again, it's not completely clear where this is going and why, but I can, at this point, I think we can sort of at least motivate what's going to happen next. The reason this on the left, I did this on the left, is I'm going to integrate this, and that's going to make that go away. And because I'm going to integrate this mess on the left, going to an inequality here makes the integration on the right quite easy. Not to mention, because there's a log here, you can sort of see that if I undo that log, I'm going to get an exponential on the right-hand side. So the next step then is to integrate this. And so we are now going to integrate from 0 to t of d. I have to be careful with the letters. I have to insert a dummy variable, d ds of the natural log of u, capital U of s, that should be an s, so I've got to be careful, and I wasn't. ds, see, it's put little brackets there, ds, and that is less than or equal to the integral from 0 to t of k ds. It's worth thinking about that line at least briefly. Why did that, can I integrate both sides and maintain that inequality? Well, it has to do with the fact that everything in sight is positive. That little u, remember, is assumed to be positive. So that means that u prime is positive. If little u is positive, then capital U, because it's its integral, is also positive. So that makes this positive. And since all we did here was just rewrite this u prime over u in a different way, that means that this is still positive. So it's not totally obvious why that's true, but it really all follows from the fact that everything in sight is positive, and that an integral of a positive function maintains the order because you're just computing area. All right, so now back to the calculations. I can now use the fundamental theorem of calculus again to evaluate this integral. The integral on the left turns out to be easy. It's the natural log of capital U of t minus the natural log of the capital U evaluated at 0. And that is less than or equal to, integrate the right-hand side, I simply get kt. So let's think about what capital U of 0 is. We want to think about what this is. Well, capital U of 0 is what I get up in the top here. Remember, capital U is defined here when t becomes 0. When t becomes 0, that integral goes away, and I'm just left with a constant. So this is just equal to c, that capital U of 0. So that's the natural log of c. And so this tells me then, when I then bring this constant term over to the right-hand side and then integrate both sides, I'm sorry, not integrate, exponentiate both sides, I get that capital U of t is less than or equal to c e to the k t. Now at this point you might think we're done, because I have shown that capital U is less than or equal to c e to the kt. And that looks very much like what the conclusion was in Gronwall's inequality, right here highlighted in green. But notice that's lowercase u, not capital U. And so I need a little u there. So how do I get how do I replace this capital U with little u? Well, let's think about that for a minute. Capital U is less than this, but by hypothesis, little u is less than or equal to capital U. So this implies, simply by using this hypothesis up at the top again, that little u of t is less than or equal to c e to the kt, which is exactly what we want. All right, so that's all of the pieces of the existence and uniqueness theorem. Sorry, not the existence and uniqueness theorem, the continuity with respect to initial conditions theorem. And I hope you've enjoyed that, and we'll stop this and post it to Moodle for you.